Hello, everybody, and welcome to another Zoom chat with Professor Jamie MacDonald from Florida Gulf Coast University. Florida Gulf Coast University. How's the campus this afternoon, Jamie, and what's the weather like?
Oh, I have a sweater on.
Yeah,
It
you do, don't you?
was way down in the 60s today.
Oh my God. Okay. All
Campus
right.
is good. It's a buzz of activity, right? Our
Yeah.
semester starts very early. This is the second week of our semester.
Okay.
And
Nice.
we also end early. I'm not sure why we start so early. Being from the Northeast, I'm used to a more traditional start time
Yeah.
later in the end of January.
Okay.
Um, I'm teaching structural geology this semester, and I'm teaching the capstone class, and they're both going well. We're we're trying to hire structural geologists, and so thankfully I won't have to teach structural
Okay.
geology. But it's in the low 70s with a breeze, and it was in the high 40s, low 50s this morning. So
Okay.
that's our winter.
Very
No
nice. Well,
no freezing fog though.
no freezing fog. Well, I appreciate you watching what we've been doing here and there. I was nice to see you in the live chat even last time. So I know you're aware of what we've been up to lately, and we were talking about the Mike Eddy model and the Jeff Tepper model and dealing with near trench magmas. But today, I mean, we can actually, you know what, Jamie? Did you have any thoughts based on the last couple of episodes about those two models? Do you lean strongly in one direction, or do you have some geochemistry that just as you're viewing that, you're like, well, man, my work, I don't know why we're talking about a spreading ridge in Southern Oregon, for instance. Any reaction generally to what we've been up to lately?
I'm very much so. I'm very interested. It's easy to get sucked in to your live streams. My wife, not maybe not this Saturday, maybe the Saturday before that goes, are there really 900 people watching this guy talk about the salts from Washington? I said, yes. Live.
Yeah,
Thousands are gonna watch later.
nice.
So so it's easy to get sucked in. Hopefully I wasn't stepping on Jeff's toes, but I was very excited to engage because I was watching and people started. I want to say hi to Joe.
Yeah.
When we worked on Joe Dragovich had a collection of tremendous scientists. Megan Anderson, Megan was one of them. Myself, I was allowed to participate. Jeff Tepper towards the end. All these wonderful people. And Joe, when he worked for the state, was great at coordinating, and we did these series of quadrangles that we talked about before. We started in the Snoqualmie, Carnation, Monroe, Lake Joy, Sultan, Lake Chaplin, Lake Rosinger, and then Granite Falls was the last one before Joe left the state, and now he's a private consultant. And and one of the things we did in 2013 is we did sort of a culmination of the volcanic rocks of Mount Persis. It's sort of
Hmm.
a clumsy name, but it's a Roland Tabor name. So, and I think highly Roland Tabor. So we'll just have to get past the fact that the name doesn't roll off your tongue. And lots of times we'll just refer to it as the Mount Persis. The Persis has some really weird geochemistry, and it's a very interesting rock. And and I will sort of jumping the gun here, but it
Go for it.
my interpretation of some of the weird geochemistry in the Mount Persis was a ridge subduction. This is
Hmm.
before the breakoff models. This is before um, you were allowed to be a Cascade volcanic arc and be that old, right? Into the
Yeah,
40s. That was a no-no,
yeah,
right?
yeah.
And so in 2013, I gave this conference presentation at I think it was a national meeting as a poster. And I have the poster if we want to look at it. And we reviewed all the ages, we reviewed the geochemistry, we reviewed the geology, and um, and I suggested that it was a ridge subduction that then transitioned into arc geochemistry.
Hmm.
And everyone's reaction was, what arc? The Cascade arc didn't exist yet. And I felt kind of like, oh, geez, because I was beginning to go into the Eocene and really the Cenozoic, because I'm a Mesozoic guy, because of the work with Joe Dragovich and the
Hmm.
wonderful collaboration he had established. So I thought, well, maybe I've gotten in too deep too quickly. Um, I feel vindicated now that Jeff has written this
Yeah,
paper
yeah, right.
because the chemistry of the rocks um, can only have formed in a continental arc and in a weird setting. Um, they have all these fancy names, but the rock that was really weird was something called an adakite. What in the world is an adakite? An adakite is it's originally named after Adak Island and the Aleutians. And the K's are two very famous igneous petrologists, a husband and wife team that worked at Cornell for a long time. The K's originally defined the adakites as the melting of the downgoing plate in a subduction zone. It is very difficult to melt the subducting oceanic crust because it's hard to get that hot below a subduction zone. As you and I know, the downgoing plate doesn't melt, it loses its volatiles like water and carbon and sulfur and a bunch of other stuff. And those volatiles act as a flux and they lower the mantle's melting temperature of the asthenosphere that sits on top of the subducting plate.
Hmm.
And then that melted mantle only partially melts, and everybody knows that partially melted mantle makes mafic magma, right? And so
Yep.
then the mafic magma rises to the surface and edifices itself as a volcano. It's very difficult to subduct or to melt the downgoing plate because you have all these other processes happening. And the K's, well, Susan is the one I know the best. Robert and Susan Kay, the K's kind of regretted inventing the term adakites because 20 years on, 30 years on now, 40 years on now, it was the 80s, 30 to 40 years on now, people were running around naming adakites all over the place. How do you make this weird adakite? An adakite's kind of like a weird um, dacite. And an adakite forms from the partial melting of a mafic rock. So you're
Hmm.
not partially melting the mantle to make a mafic magma. You're partially melting a mafic rock. But it doesn't have to be basalt or gabbro. You can melt amphibolite too. So mafic is a type of magma that's rich in iron, magnesium, and calcium. And when you melt the mantle and make a primary magma, you partially melt the mantle to make a primary magma because you can't melt the mantle completely. You make mafic magma. Think of Hawaii. Think of all the black sands and basalts in Hawaii. Think of Greenland, Iceland. Sorry, Iceland. Think of Iceland. The current news is getting me confused. Think of Iceland and all the black basalts that are forming there. Those are formed from partially melted mantle and they're mafic in composition. If you melt a basalt or you melt a gabbro, which is the intrusive equivalent in the magma chamber, or you take those two rocks, you metamorphose them into an amphibolite, you're going to make this weird rock called an adakite. So it's kind of like when you were talking about the Bald Mountain and the Mount Persis, how they're melted crusts, there are these weird things called Peraluminous magmas. You're melting crust to make these rocks that are made up of magmas that are oversaturated in aluminum. You're not melting the entire crust. Now you're melting a very specific thing. You're melting something that's mafic. Okay, sorry about that.
That's okay.
Mount Persis has these adakites in it,
Yeah.
and they're a very unusual rock type compositionally. And you can only form them where you melt mafic rocks partially into a magma. And you can do that in a bunch of different places. You can melt the base of a volcanic arc because the base of a volcanic arc is very mafic. You can melt the downgoing plate, or you can do it in a ridge subduction setting.
Hmm.
So I think it was Mike told you about the Chilean ridge. I have a slide up that shows the position of the Chilean ridge. It actually shows a bunch of places all over the earth. If you don't mind if I share my screen,
Go for it.
it shows a bunch of places all over the earth where you have ridge subduction.
Hmm.
And down here where the Chilean ridge is subducting, some of the rocks that are forming down there are adakites.
Hmm.
And this is slightly different than, say, where the Juan E. Fernandez Ridge is subducting over here, or where the divergent plate boundary between the Cocos and the Nazca Plate is subducting over here by the Galapagos hotspot. So down here you have some rocks forming that are really unusual. They're kind of weird. They're adakites. And so the Mount Persis has these it has these unusual geochemistries in it. Let's take a peek at a slide I made that shows these unusual geochemistries. You know what's better? Let's not do that. Let's look at a map that shows what's going on. No, let's not do that either. Let's just talk. Let's so another thing that the Persis has in it is it doesn't have typical arc rocks. It also has emorbs in it. Enriched mid-ocean ridge basalts, which you don't form at a convergent tectonic setting, you form that at a divergent plate boundary from shallow melting of the mantle without water present. So, okay, so we're studying the Mount Persis. I'm finding these normal geochemistries, and then every once in a while, I'm starting to find weird geochemistry. And so okay, there's all these geochemistry in the Mount Persis. The Mount Persis has geochemistries that's very typical of continental arcs, but it also has these enriched mid-ocean ridge basalt geochemical affinities, which you would normally find at a divergent plate boundary, where the asthenosphere is just rising up from below to fill in the space, and it decompressively melts and makes a magma, mafic magma. Or and I'm finding these adakites. And the only way you can get all of that happening is if you have a subduction zone that also has a divergent plate boundary in it, a ridge, because the ridge is going to give you a window where the asthenosphere can sneak through the overriding plate, decompressively melt, and make something that looks like an emorb. And then the divergent plate boundary, as it's subducting, well, can also generate adakites. So I said that that there was a ridge subduction occurring during the Mount Persis volcanic rocks forming. What we did not have is control over the ages. We don't know if the continental geochemical signatures are younger than the weird geochemistries or if the ages are all over the place. We don't have control over that. Because in a perfect world, you would kind of want the ages to group together. The weird stuff should be one age, and the normal continental arcs could either be before, during, or after, and things like that. So that was a very long answer to say yes, I do like a subducting ridge during the ESC.
Okay, well let me
Yeah,
call back what I think I'm hearing,
sure.
and I always get Pilchuck and Persis mixed up. So
Mhm.
I thought we were maybe done with the break off versus slab window versus other things because we left Pilchuck and
Yeah.
Bald Mountain behind.
Yeah,
And
Persis is
once
younger. Persis
yeah,
is
and
younger.
once we drop down to Persis, I mean that. Let me show you a couple quick things to tie to
Please,
what I'm building to here, Jamie.
let's do.
So I thought once we got to Persis, we were in the volcanic arc. We were in blue. So this is a slide that I'm using as a guide for the next couple
Hmm.
of episodes,
Right.
and we have. I literally zoomed in here so that I can keep these straight. Oh, I'm sorry, I did it here. So Mount Pilchuck Stock and Bald Mountain,
Right.
too old. They're like
They're over there by
49,
Granite
50.
Falls. Yeah.
Yes.
And
And that's what Jeff and Mike were talking about. Like Jeff wanted it to be break off belt, leaned heavily in that direction. Mike Eddy leaned towards slab window. Now you're down here at Mount
mhm.
Persis Volcanics, and we're young. I know that Jeff's only picking one number for the purpose of his slides, but there's quite a range of ages, it
Yes,
seems like.
there is.
Yeah.
There is quite a range. We it starts around 47, the
Okay.
Mount Persis volcanics, and they don't end until close to I have a figure that shows it. Like now I need to cheat and read it. They don't end until about 36. So it goes from about
36.
47 to 36.
So it's
And
almost like I'm disappointed, Jamie, because I thought once we turn on the volcanic arc, we're done with that debate. But you've got
yeah,
evidence somewhere in this window of 47 to 36 that you might have a subducting spreading ridge. Is that what I'm hearing?
well, there's something going on that's allowing the mantle to move up towards the surface of the Earth without the presence of a slab, because you
Huh.
can't get enriched mid-ocean ridge basalts any other way. And there's something going on to create these adakitic compositions. So the some sort of mafic source is melting to create these weird rocks called adakites after Adak Island and the Aleutians. And so
Okay.
something happens, something's
Yeah.
happening, and it's over though by the time, and you don't see it in other places. When you look at the geochemistry of rocks that are not that much different in age, like the Hanson Lake rhyolite or the Granite Falls stock, the geochemistry. It's just the Mount Persis.
Okay. So this is great. This is where I wanted to
Mhm,
go today.
mhm.
So there's a handful of names
Yeah.
potentially tied to Mount Persis volcanics. There's
Oh, there are a
plutonic
lot of names.
equivalents.
Yeah.
Can you just it's been a while since you've studied those rocks, I think, but like
I,
Young's whatever and
yeah.
whatever, like can we group a few words that all tie to this Persis topic that we're talking about right now?
The Mount Persis is a really interesting unit. I really enjoyed working on it, mostly because I got to work with Joe Dragovich, who is the Croatian sensation. And let me, if I'm allowed, let me share
Go,
a
man. Yeah.
map of the Persis.
Thank
And
you.
so there's a little inset map here to show everyone. I apologize, my cursor's not working well because it's a PDF file, but there's a little inset map here of Washington State. I
Yep.
I wasn't ready ahead of time because it's orange, but all of the orange should have been blue, right? All
Yeah.
of the orange is Mount Persis.
Okay.
And the Mount Persis unconformably sits on top of the Western Melange Belt,
Okay.
right? Uh, there are several of the larger igneous features here that are red. One to the northeast is called the Youngs Creek Intrusive Complex. And,
Okay.
and Roland Tabor originally thought that might have been part of the Index or the Grotto Batholith. Um, it turns out it's not, it's too old. So
Ah,
we drove up there and we got some samples of it. It had one of your favorite igneous features in it. It has mafic enclaves.
there you go. Good.
and
Good.
it's a hornblende granodiorite, and it has a bimodal age. It's 39 million to 42 million years old. So it was just magmatically active over a long period of time. Then way down to the south, Tabor, when Roland Tabor was doing his exquisite mapping, they got a potassium argon age on what's called the Fuller Mountain Plug at 47 million years old. And that's down here.
Okay.
Um, Not shown on the map are several other igneous features, and one of them is that beautiful Drunken Charlie Lake, right? Ken Dragovich name units, right? So the Drunken Charlie Lake is in the 40s. It's 47. I looked it up. Then there's another one called the North Fork Creek Intrusive Complex, which we don't have an age of. The the North Fork Creek is gabbroic to diuretic to felsic. The Drunken Charlie Lake, and then another intrusive complex that we didn't name to the south of on the southern part of the Mount Persis. These were dacitic domes that were collapsed. So we have five or possibly more volcanic centers: the Youngs Creek Intrusive Complex, the Fuller Mountain Plug, the Drunken Charlie Creek Lake, the Drunken Charlie Lake, the
Yeah.
North Fork Creek Intrusive Complex, a couple of unnamed igneous bodies. These are the volcanic centers that were erupting and making the Mount Persis over this 47 to 36 million year old period. So that's why there's all these names, because there are all these volcanic centers that are left over that were the magmatic systems that were erupting, because the Persis are a bunch of extrusive igneous rocks. They're rhyolites, they're lava flows, they're tuffs, they're pyroclastic rocks, they're sedimentary rocks, there's sandstones and conglomerates in the Mount Persis. There's fossils, there's a lot of plant fossils in the Mount Persis and stuff like that. And so it's a very it's a really interesting group of a lot of collected rocks, mostly volcanic rocks. There's sedimentary rocks in there. There's igneous rocks in there. Um, there's all sorts of stuff, and there's lots of different types. And so you have all these units that are all around the same age, and they're erupting and depositing the Mount Persis volcanic rocks on top of the Western Melange Belt, and then we were able in our geologic mapping to see that towards the west they're starting to thin out, and so they started to intermix with other units that are Eocene age off to the west.
So, a couple things. Love this detail. Thank you.
Mhm.
And of course, what I try to do is just grab a few things that I feel like can build a narrative. So
Yeah.
between 47 and 36, the chemistry is just bizarre all through that stretch of time, or is there any things are arc-like and then they become non-arc-like as you go younger? Or is there any kind of
We don't,
trend within that 11 million
that's an
years?
excellent question. We don't have control on when these weird geochemistries occurred.
Hmm.
After the fact, we thought, oh, if we could go back and do some more age dating, we would go out and relocate these adakites and figure out how old the adakites are.
Yeah,
Because it's very possible that the weird chemistries are closer to 47. And that as you get closer and closer into the 30s, things sort of normalize, right? And you turn into a normal volcanic arc.
right.
Um, it's also possible that the weird chemistries are various ages all over the place. Um,
Okay,
but we
you
don't have
want
good control over that. We looked at them spatially. I do have a map of that, although it's not going to fit very well on this format. But we looked at them spatially, and they're kind of all over the place spatially. That doesn't mean that much, because you're looking at lava flows. Lava flows are incised by a number of rivers. Some of the river systems are quite large. Um, uh, like the
Mhm.
Snoqualmie and the Pilchuck and all these different things, right? And so, but uh, but we don't have good age control over the we don't have any age control over the geochemistry of the rocks that suggests something weird was happening versus maybe just a normal continental arc.
Okay, so I'm going to share my screen, and I'm
Mhm.
wondering, I know you're talking about your detailed work here in the
Right.
Persis neighborhood. Uh, do you suspect, or do you think it's possible, just because people haven't done it, if people go to Tukwila or Northcraft or Goebel, there will be the same bizarre stories that you've pulled out here? Or do you think something truly is bizarre here compared to the rest of these early Cascade Arc rocks?
That's a very good question. And I'm not sure. I remember Jeff had a paper that I liked a lot. And let me because we did do detailed work in the Hampton Lake rhyolites and the Granite Falls, and they don't have any geochemistry that would make you scratch your head or go, "Ooh, something weird's happening." Um, oh, I know. I'm sorry, I'm looking in the wrong place. Gray? Jeff studied the
Gray's Rivers.
Gray Rivers. Don't I'm not sure about their age, but they have a weird geochemistry.
They do, and that's part of what I'm going to try to do tomorrow. I think that I love a couple of maps that I've found that show the clockwise rotation and show Yellowstone mantle plume signatures, and I see that Grays River and the Tillamook across the river down in Oregon as being rotated up from the south, and I'm just staying away from those guys. Like we have turned down the Cascade Volcanic Arc. It's 46 million years ago. We've got light blue. We're ready to go, and I'm realizing that the Persis family, I guess
Persis
that's
is
what I'll
weird.
call it,
Persis is
is
weird.
is is weird and not a well-behaved early Cascade Volcanic Arc, I guess. Like if we're
The
really
um
going,
the Granite Falls and the Hanson Lake are better. They're
okay,
more behaved. They have all the geochemistry that you would get in a normal continental arc setting. And
okay,
they're basically the same age. The Granite Falls stock, we got an age of about 40. I think it was Mike Getty's age actually. We have an age in our report of about 45 million years old.
yeah,
And then the Hanson Lake rhyolite, we got an age of 43 million years old.
okay,
And when we started studying the Hanson Lake rhyolite, people thought the Hanson Lake was the extrusive volcanic equivalent to the Bald Mountain and the Mount Pilchuck because the Hanson Lake is Peraluminous. For those of us who are normal people and don't know what the heck that means, when you make a magma has a normal amount of aluminum in it, and we use the word meta-aluminous. For normal? That's not what meta means, but we use the name meta-aluminous for a normal amount of aluminum. A magma that's meta-aluminous is oversaturated in aluminum. What in the world does that mean? It means it has too much aluminum in it. And when it starts to crystallize minerals, it has to start to crystallize minerals you won't normally get in a magmatic rock that you normally get in metamorphic rocks. So it'll make garnet, magmatic garnet. You normally don't get garnet in igneous rocks. Normally, garnet forms in metamorphic rocks like schists. You can get cordierite, you can get kyanite, you can get muscovite. Muscovite is actually a very rare mineral to get in an igneous rock. You
hmm,
normally make biotites and amphiboles, and by the time you get done making biotites and amphiboles, just think Bowen's reaction series. You're now all the way down at the end of the Bowen's reaction series. You can finally make minerals that are rich in potassium. You've already used all your aluminum. You used your aluminum when you were making the iron and magnesium rich amphiboles and biotites. So a potassium aluminum mineral like muscovite, you tend to run out of aluminum. You can't really make it.
hmm,
So that's why when you look at tonalites, there's no muscovite. When you look at granodiorites, there's no muscovite. But when you look at granites, lots of times there's muscovite because lots of times granites are produced by melting crustal rocks. And so the Pilchuck, the Bald Mountain, they got muscovites in them,
hmm,
right? The Hanson Lake rhyolites have garnet in them, and geochemically they're peraluminous. So based only on the geochemistry, because people didn't have a good idea of the age, they said, well, these must be the extrusive equivalents of the Bald Mountain Mount Pilchuck, because Bald Mountain Mount Pilchuck have too much aluminum in them. They're oversaturated in aluminum, and they have these funny minerals in them, like igneous garnet. Hanson Lake rhyolites are they're metaluminous and peraluminous, but some of them have garnet in them, and so they must be equivalent to the Pilchuck and Bald Mountain. And then we got an age. Oh no, wait, oh, they're too young.
right, yeah,
Yeah.
exactly,
And
yeah,
they're right next to the Granite Falls stock, and
yeah,
they're the same age. They're basically the same age. Now the Granite Falls stock is not peraluminous. Granite Falls stock is a normal, has geochemistry that you would expect a normal continental arc to have.
right,
However, the Granite Falls stock is cut by a number of really interesting um, igneous bodies. And Dragovich made this, Joe made this really simplified figure that's good to show people. So here's the Granite Falls stock
hmm,
in these pinks, right?
yep,
These pinks are the Granite Falls stock. The Granite Falls stock is a 45 million year old granodiorite with mafic enclaves that Jeff Tepper took you to. And it occurs along several rivers, right? Here's one of the rivers, right? Structurally, it's bounded by faults. you can't see an intrusive relationship between the Granite Falls stock and the Western Melange Belt anymore because it's structurally controlled.
Mhm.
And within those um, faults are these weird igneous features like dikes. The dikes are intruding the Granite Falls stock. The dikes are intruding the fault zones. The dikes are intruding highly sheared Western Melange belt. There's Joe Dragovich in the picture. Hey, Joe.
Mhm.
Um, and these dikes that are the same age as the Granite Falls stock and have this co-magmatic relationship to it, they're peraluminous. They're
Mhm.
oversaturated in aluminum.
I see.
So there's so the oddities about the Granite Falls stock and the Hansel Lake rhyolite is that it's oversaturated in aluminum. And you can do that through two ways. You can melt the crust. We didn't make those rocks by melting the crust, or you can assimilate a large amount of crust as you're coming up the from the mantle through the lithospheric crust, through the continental crust, and then erupting to the surface. There might be assimilation, um, but other than that, they're pretty straightforward.
I'm having fun. I've got an idea.
Yeah.
For us to wrap up, I want to draw something and I want to talk to you while I'm drawing. You're going to coach me up as I draw this thing. But
Oh boy.
if this works, I might try to do this on
The one thing
tomorrow's.
I wanted to talk to you
Yeah,
about that is very
yeah,
interesting. If you bring
sure.
back up your blue, right, your figure that shows the blues, all the colors
Good.
on it.
Yep.
One of the things I like to think about is tectonically is the position of volcanoes with relationship to the subducting plate that lies below them, right? There's this concept in tectonics called an arc trench gap, right? So if
Yep.
you go from the 40s
Yeah.
into the Oligocene, right? So if you go from places like Granite Falls stock and the Hanson Lake rhyolite and the Youngs Creek intrusive complex and the Drunken Charlie Lake and the Mount Persis, the the Cascades are starting there, but then they migrate inland to where you have the Index and the Grotto and the Snoqualmie batholiths,
That's
which
what I
tell,
was that's what I was about to draw, man. This is
oh
perfect.
man, look at
We're in
this. Look at
sync.
this.
This is
So
good.
it tells me that the downgoing plate is shallowing and it's forcing the arc inland, right? Because the volcanic arcs have to be 100 to 150 kilometers above the downgoing plate because that's the sweet spot where the downgoing plate loses its water and other volatiles. It hydrates the asthenosphere that sits above it, partially melts the mantle, and then the mantle is hotter than the rock that surrounds it and less dense than the rock that surrounds it. So it rises up towards the surface of the earth, edifices itself as a volcano, right? It has to be 100 to 150 kilometers. And as this is the downgoing plate, this is the overriding plate. As you change that dip of that downgoing plate, the arc's going to move around. And so during the 40s, there you have all these nice blue rocks in the 40s. I apologize, mine were orange. You have all these nice blue rocks into the 40s. But then when you get to the index and the grotto, everything shifts to the east. So that tells you something's going on. Subduction, the slab might be shallowing, or for some reason the volcanic products are shifting to the east. Then the modern arc is out to the west, right? That's what's going on with this slab, right? Is this slab you were going to do something? Please
Something
do.
slightly related to that,
Yeah.
uh, I'm hesitating because I don't know if I should. I'll save it for tomorrow. What I want to do is this. You're very good, Jamie. This is so engaging, and when people next time see you in the live chat, they'll go, "Oh my God, that's that guy from
That's
Florida.
that
Yeah,
guy.
he's fun."
That wimp who
Um,
wears sweaters when it's 60 out. That guy.
okay, so this is a throwback to the first few letters, and I'm not even sure if you were with us at that point, but
Well, I watch them in afterwards normally.
yeah. So we had the Western Melange Belt, we had the Grello,
Hmm.
and we had all this Arcosic melange Focus, please. I'll throw in some yellow to make this grello. The Western Melange Belt, as we're building the basement and the crystalline cores off to the east. And then I forget which letter it was, but I came up with this idea that I guess we have a parade of plutons coming up
Hmm.
through this grello. We have Granite Falls, and we have, well,
All
that's
the
one I
Persis stuff, all the Persis stuff, because the
Well,
young.
well, that's my point. That's my point. So let me
Yeah.
get to my point here first. I'm going to grab some green. By the time we get to the index, we're into green, which is the 30s, and
Mm.
Squire Creek is, I guess, north of that. And if I make so, in other words, I have a well-behaved 45 million year old early Cascade arc, Granite Falls,
Granite Falls.
and
Granite Falls is behaving.
And I our ind this is what I'm wanting to ask you. Do you know anything about Index or Squire Creek in the 30s, which is also in Western Melange Belt? Are they also well behaved? I don't even know the numbers yet, but it's in the 30s somewhere. And then I want to skip over Persis since it's
Mhm.
a bastard stepchild of this family here.
Persis might be something that's transitional. Transitional
Okay.
between um all the really cool things that were probably happening as a response to Silesia and
Okay.
ridges and the resurrection plates and India crashing into Asia to make the Himalayan mountains, causing the plate boundaries between Australia and the Pacific plate to change direction, causing the Marianas Arc to rift open and create the Marianas Basin, right? There's all these wonderful things happening globally in response to plates moving direction. The Hawaiian Emperor Seamount changes. Washington is involved. Isn't that wonderful and nice and important? And and then you transition to a normal arc setting over time. And Persis might have captured that transition because it starts in the very late 40s, 47-ish, and doesn't end until the index intrudes it, right? The index batholith intrudes the Mount Persis. And one of the things that is really interesting and popped in my head as soon as you and this is related back to when we
Yeah.
when we talked a while ago about the Western Milan belt and how it's related to Hannah's work is when we did ages on some tufts. These are our ages for two tufts from the Mount Persis. This one's 36 million years old, but it has all these much older zircons in it. This one is 44 million years old, but it has all these older zircons in it. And these are Peraluminous tufts. They're tufts that are oversaturated in aluminum, and they have zircons in them. So they're igneous rocks, and they have zircons in them like you would see in a detrital sandstone, right? They have all these older ages in them, a lot of Mesozoic ages and Precambrian ages. And my interpretation that we put into Dragovich's uh, um, pamphlets that came with our maps was that this was a simulation of the Western Melange Belt and the other crustal units as the volcanoes were coming up and erupting. And so the Persis is also intruding the Western Melange Belt. It's got a meaningful relationship to it. A lot of the zircons from the basement are getting entrained in these tuffs and erupting. I didn't work on the index. I don't know very much about the grotto besides what they are. We did work on the Snoqualmie. We worked on the Snoqualmie in 2007,
Oh,
2008. And
okay.
I remember the chemistry being pretty straightforward, um, except there were Shoshonites.
Oh boy.
I got nothing but weird names for you today. These are igneous rocks that have very high potassium.
Okay.
And I remember being puzzled. They normally don't form in that kind of setting. And I don't remember why and how we resolved that. We might not have. But we did, but for the most part, the snow colony was very straightforward. We were working off of a man's master's or doctoral thesis from like the 50s or 60s, whose name I can't even remember. I'm ashamed I can't remember it because the poor man did all that work and I can't even remember his name off the top of my head. Might have been Edwards or something.
Okay.
Um, and uh, and this was in the Snoqualmie batholith map, and we have all this nice geochemistry and stuff like that. And we found, oh no, those were younger. Never mind. We found a really cool Lahar deposit, but it wasn't related to the Snoqualmie.
Okay. Okay.
And now the one thing I can tell you about the Granite Falls stock and the Youngs Creek intrusive complex is I had undergraduate students um, geochemically analyze the amphiboles from those stocks, and they used geothermal Ooh, they used the chemistry of those minerals to estimate the temperature and pressure at which those stocks formed, and they were both shallow. They were both about at the same level, and so they're occurring at about the same time at about the same level. Um, but it's interesting that
Yeah.
the Mount Persis has these weird chemistries in it, these adakites or adakitic rocks, these emorbs, and then it's got normal chemistry that you would expect in a continental arc. Again, I feel vindicated by Jeff Tepper that it is a continental arc because it in 2012 or whatever, everyone, oh, no, 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 no.
Oh, yeah. You've stuck around long enough to see the vindication. That's good.
Well,
I'm gonna go ahead.
part of me feels like I never finished working on them because I thought, oh, I must have screwed something up because everyone's telling me the continental arc didn't start yet. But we did work on the Snoqualmie. I remember it being pretty straightforward. There was a handful of samples that had very high potassium, which were kind of weird.
Yeah.
But for the most part, it was pretty straightforward.
Very good.
Yeah.
Jamie, thank you for your time today. Hold the line, please. We'll
Oh,
talk a
you
little
got
bit
it.
after I stop
You
recording,
got
but
it.
a
I'm
pleasure as always to visit with you. Thank you.
sure.